Very good afternoon, everyone. Right now, we are in the week 12 of the Introduction to Material Science and Engineering course, which is the last week. Today, we are going to discuss about the list of the content that has been covered in this particular week. We'll try to solve few questions based on which you can solve the assignment question very easily, which will going to be which will going to assist you in solving this assignment question. So before we begin, let's have a look onto the list of the content that has been covered in this particular week. Here, we discuss about the two stress and two strain, how we can calculate them from the engineering stress and engineering strain. For example, let's say we are talking about the two stress, which is given by the engineering stress time 1 plus engineering strain. Similarly, for the, if someone wants for the two strain, it is given by the log of 1 plus engineering strain. So on the right hand side, we can see only the engineering term is there, and on the left hand side, we can say there are the true terms. If someone is aware about what is the engineering stress or engineering strain, they can directly find what is true stress and true strain from that. Then we discuss about the creep, under what condition practical application, in daily life we see the creep, and then we discuss about the factor which is affecting the creep, that is stress and strain. Sorry, the stress and the temperature. Then we saw the mechanism of the creep. After that, we went to the composite material. Like till now, our discussion was majorly focused on the structure of this metal, ceramic. We're not concerned about the composite. We're not concerned about the model, the mechanical strength of the composite and all. So here we discuss about the what is the young modulus of the composite will be. We saw the two different cases, isostress and isostrain. In both the cases, we saw that how the modulus of a composite going to be vary. Later we move to the fracture and the fracture of the material, where we discuss about the ductile to brittle fracture. Then we discuss about the role of the crack in the specimen. Then we discuss about the brittle material, the Griffith criteria. Later on we discuss about the stress concentration, like even though we are applying the certain force, certain stress to the material, the stress acting at the different location is different because of the presence of the crack. So at the crack tip, we found that there is a maximum stress which is present, and that is the one which is responsible for the propagation of the crack. Then we discuss about the ductile to brittle transition temperature, and then how we can enhance the fracture resistance, talking of the glass and all those things. And at the last, our final topic was the fatigue and how the propagation of the crack is take place in the fatigue. We know that in the fatigue test, we apply the considerably lower stress compared to the yield stress, and still the specimen is going to be fractured after a certain interval of the cycle. So it's a cyclic loading question. Okay, so these are the list of the content that has been covered in this particular week. If you have any doubt, you can please let me know. If not, let's move ahead to the next question. Let's move to the question number 1. We will try to solve few questions based on this. The first one is a true and false based. Let's start. The true stress is always greater than the engineering stress in tension. So they are talking about the tension. And we have to comment on the true stress and true strain. Sorry, true stress and engineering stress. We know the formula. True stress is given by the engineering stress times 1 plus engineering strain. For tension, we know that engineering strain is greater than 0. It's always positive, right? Since we are talking about the tension, let's add 1 on both the sides. So it will be 1 plus strain will be given by 0 plus 1, that is 1. Let's multiply the, again we are giving the tension, right? So the sigma is a positive term. The sign of this particular, this sign will be, it's going to be the same. So multiplied by sigma multiplied by sigma. So what we have got is engineering stress is less than, this term is nothing but the true stress. So in the case of tension it is correct. In the case of tension, the true stress is always greater than the engineering stress. So the first answer is true. The volume constancy is a valid assumption for both elastic and plastic deformation. Volume constancy is valid for both elastic and plastic deformation. It is incorrect. It is valid in the plastic deformation, but it's not valid in the elastic deformation. The volume of the specimen can increase in the elastic deformation because we know that it involves the bond stretching. If we are talking for the tension, so the volume is going to increase while it will decrease for the compression. So the answer is false. For the plastic deformation it is valid, for the elastic it's not. Now, a true strain provides a cumulative measure of the deformation regardless of the path reversal. In the class we have saw that we took the length of a bar of length L, then we deform it to the 2L, then again we compress it back to the L. So overall there should be the no net strain in the material, while engineering was giving the strain of negative of L, while the true strain was giving it 0. So even though like this path reversal which we took, the engineering strain was not able to give the significant value which we are looking for, while the true strain is giving the valid value. The path reversal is considered under the true strain. So we can write that as true. Okay, let's move to the next question, question number 2. In the demo, the lead tin solder spring crept at room temperature because. So we saw that in the demo, in the class, that there was a two spring. One is a lead tin and another one was a, let's say, I think aluminum or tungsten, which we hanged, and we found that at room temperature this one crept, well this one not crept. Why it's that? We know that if the service temperature divided by melting temperature is greater than 0.5, then the things is going to creep. The melting point of lead tin was considerably lower compared to the other aluminum or tungsten, we can say, and that's why it's going to creep at the room temperature. So the right answer, its melting point is low. So the option A is the right answer. Okay, so with that we have solved this question number 2. Let's move ahead to the question number 3. With melting point given in the bracket, these are the melting point of the material. Take those material which will creep significantly at T equal to 180 degrees Celsius. So service temperature is given to us, that is 180 degrees Celsius. And we know that service temperature divided by melting point, if it is greater than 0.5, the things is going to creep, and we want that the creep only. Like the answer, like the what material which we are looking for is it should creep at this particular temperature. So let's try to find them. Let's put the service temperature 180 degrees Celsius, but again we don't put temperature in the degree Celsius. We'll add 273 over here, divided by melting point greater than 0.5. We can exchange their position. So what we will get, 180 plus 273 divided by 0.5 should be the greater than melting point. Let's work it out. So it's 906. Again, it's in the Kelvin. So what we have to do, we have to convert this to the degree Celsius, because all the brackets is given in the degree Celsius. So for the material having the melting point is less than 633, they are going to creep. Okay. So which are those material? The material are lead having the melting point 633, and more or less we can say that maybe aluminum can also creep. They are more or less very near to each other. So now if the question is MCQ, I will only select option A. If the question is MSQ, I will select A and C both. Okay, so with that we have solved this question. Now let's move ahead to the next question, question number 4. If the melting point of polyethylene is 140 degrees Celsius, it will not creep at more or less same type of question. Here now melting point is given to us, that is 140 degrees Celsius. It is not going to creep. So when it will creep, the temperature divided by the service temperature divided by the melting point of the material should be greater than 0.5, then it will creep. While if we reverse it, it's not gonna creep. No creep. Melting point is given to us, that is nothing but 140 plus 273. We'll convert to the Kelvin. So now let's work out. Let's work it out. So what we will get, 0.5 multiplied by 140 plus 273. So here we got the temperature of 206.5. 206.5, it's in the Kelvin. We have to convert this into the degree Celsius, so that the temperature, so now if the service temperature is less than 66.5 degrees Celsius, then it's not going to creep. No creep will observe. Room temperature is more, right? We want less temperature, so it will creep. We don't want this also. 60 degrees also is not desired, so only the right answer is minus of 196 degrees Celsius. Okay, I think somewhere around this only the liquid hydrogen temperature is also there. Okay, so with that we have solved this question number 4. Let's move to the next question, question number 5. For a given material, doubling the applied stress at constant temperature will halve the steady state creep rate, creep rate. Okay, so mostly we are talking about the creep rate, steady state creep rate. We know the formula for the steady state creep rate is that steady state creep rate, which is a function of the temperature and the stress, is nothing but constant times sigma to the power of n times exponential of minus of q divided by r t. Right now we are talking about constant temperature, so this factor is constant. So this factor we don't need to consider. C is also constant, so this is also we don't need to consider. What we are concerned is about is that only the stress. So for a given material, double the applied stress. Let us say that applied stress is double. So initially let us say sigma 1 was there. Right now it's sigma 2, which is 2 times of sigma 1. So in that case, what we will get? The steady state creep rate for the case number 2, steady state creep rate for the case number 1. We can write them as, this is going to cancel out. What we will get? 2 to the power of n. So the final steady state creep rate will be equal to the 2 to the power of n times the initial steady state creep rate. So increase creep rate by the factor of 2 to the power of n, where is the n is a stress exponent, right? So with that, we have solved this question number 5. Let's move to the next question, question number 6. Cross slip. So cross slip, we know cross slip can occur in the screw dislocation, where if they are moving if a screw dislocation was moving in one of the plane, but it encounters some inclusion over here. So what it will do? It will see that it will search for some other path. So instead of moving, so this dislocation, instead of going in the forward direction, now it will bend and it will go in the failure direction. This is known as the cross slip, and the screw dislocation changing the slip plane 1 to slip plane 2. So now climb is done by the edge dislocation, we know, right? So the edge dislocation movement perpendicular to the slip plane. Perfect. Diffusion creep, we know that it is a stress assisted atomic migration, right? So more is the stress, more is the diffusion creep. Grain boundary sliding, it's a viscous like movement at the high temperature. So with that, we have solved this question number 6. Let's move toward the question number 7. The creep deformation, true and false based. Let's do it one by one. Creep deformation can occur even at the constant stress. That is true. Perfect. You remember, like in the case of spring, we not suspended any weight. This was deforming under its own weight, right? So it's true. Diffusion creep require dislocation motion. No, it's not the case. It doesn't require the dislocation moment. Diffusion creep is mostly about the vacancy, so it's a false. Grain boundary sliding is more prominent at low temperature. Grain boundary sliding, which is not the case. Just a moment back, we saw that grain boundary sliding is a viscous like movement at the high temperature. It takes place at the high temperature. So again, it's a false. To make it true, we can replace low with the high. In climb, where we talk about the edge dislocation, vacancy assists in the movement of the edge dislocation. That is correct. Due to the vacancy moment, only the dislocation can climb. So with that, we have solved this question number 7. Now let's move ahead. Let's go to the question number 8. Now, for a glass fiber reinforced polymer composite with matrix modulus is given to be the 2 GPa, fiber modulus is given to be the 70 GPa. What is the composite modulus of the composite? So what has happened over here? We had a composite. Again, we are talking about the isostrain. Here we added some fiber. And this was the polymer. The polymer modulus is given to us, that is 2 GPa. This fiber's modulus is also given to us, which is 70 GPa. Now they are telling that if by the volume, if you are adding the fraction of the polymer, fraction of the fiber is 0.5, like 50% fiber is there, 50% matrix is there, polymer is there. What is the modulus of the composite under the isostrain? We know that in the case of isostrain, the modulus of the composite is given by F times fraction times modulus of the fiber plus 1 minus F times modulus of the matrix. So we can substitute this value. F is given to us 0.5. So 0.5 multiplied by the EF, that is 70, plus 1 minus 0.5 times PM, that is 2. So half of 70 is 35, plus again this is half of 2, which is 1. So answer is 36 GPa. We can see that the matrix was 2, fiber was 70, their combination is lying in between them, 36. Okay, so now let's move ahead to the next question, question number 9. Let's focus on the first part. The isostrain model predict higher modulus than the isostress model for the same app. See, we know that isostrain model composite will be given by the modulus of the composite will be given by the modulus of the fiber plus 1 minus F times modulus of the matrix. This is isostrain. For the isostress, we know that it is given by the F divided by modulus of the matrix, sorry, modulus of the fiber plus 1 minus F times modulus of the matrix. Isostress. If one draw this, here on the y-axis modulus of the composite, on the x-axis the fractions of the fiber. For isostrain, it is given by the linear. While for the isostress, it will be more or less like this. So if we talk about at the same F for the constant fraction, we can see that isostrain is giving more value than the isostress. So isostrain model predict higher modulus than the isostress model for the same F, that is true. Second one, the isostress condition required the matrix and the reinforcement to have the identical modulus. That is not the case. They should have a different, they must have a different, they can have a different, right? So it's a false. In the isostrain model, EC increased linearly with the fiber volume fraction. That is true. For isostrain, it is increasing linearly. It's true again. The isostress model equation is derived assuming equal strain in all the phases. No, not equal strain. It is equal stress. Isostress, right? So here we assume that the equal stress is applying on to the different phases. So with that we have solved this. So it's a false. True, false, true, and false. Let's move to the question number 10. A continuous and aligned glass fiber reinforced composite consists of the 40 volume percent glass fiber having a modulus of the elasticity 69 and 60 polyester resin that has the, when hardened, display the modulus of the 3.4 GPa. Compute the modulus of the elasticity for this composite in the longitudinal direction. Again, the longitudinal direction, it means that this is the isostrain. For the isostrain, we know that we can apply this formula. Let's substitute all the values. 0.4 multiplied by 69 plus 40. This is 0.4, then it will be 0.6 multiplied by 3.4. We'll get the value from here. Let's do it. $29.64. The unit will be same, GPA. Okay, so with that we have solved this question number 10. It was more or less similar to the last question which we have solved. Let's move to the question number 11. Which type of fracture absorb more energy before failure? Ductile, brittle, both absorb the equal energy, neither absorb any energy. We saw that when we talk about the brittle, stress strain curve, it will fracture somewhere over here. While if we talk about the ductile, it will go something like this and then fracture after a while. So here the energy absorbed is this much, while here the energy absorbed is this much. So in which case it is more, it's very clear that ductile will have more energy absorbed compared to the brittle material. Okay, so let's move to the next question. Question number, okay, I made a mistake with the question number. So now, how did the stiffer paper behave compared to the floppy paper having the same crack size? In the class, professor demonstrated us the two paper. One was the floppy one, another one was the stiffer one. Both of them were having the same crack size. But when he tried to tear them, he concluded that what we got to know that like the one which is stiffer is required more fails to tear compared to the floppy paper. Okay, this was the observation which he made. Let's talk about this question. A sample of glass have a crack of half length 2 micrometer. The Young modulus of the glass is given to us and the specific surface energy is given to us. Estimates its fracture strength and compare it with its Young modulus. In fact, let's do the first part. Fracture strength we have to calculate. Sigma F we have to find. It's for the glass. Glass we know it's a brittle material. So we can apply the Griffith criteria. It's given by 2 root over 2 gamma E divided by pi times C. What in all the other things that is given to us? Root over 2 multiplied by the gamma, that is surface energy, that is 1 joule per meter. We'll write everything in joule per meter. Okay, so we don't need to worry about the units. Modulus, the modulus, Young modulus is given to us as 70 giganewton. So 70 multiplied 10 to the power of 9. Again we are talking about the newton, so no need to worry about it. Divided by pi 3.14 and C is the crack length. What is given to us is that the half of the crack length. In class we saw that crack length, we denote crack length by 2C. What is given to us is the half of the crack length, that is half of this. the value of C is given to us, so we can directly write the value of C, that is 2 micrometer. 2 multiplied 10 to the power of minus of 6. Let's try to work it out. Root over, sorry, root over 2 multiplied by 1 will not consider 10 to the power of 9. 0.14 multiplied by 2 multiplied by 10 to the power of minus of 6. So let's try to find 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Okay, so this is what we have got. The fracture strain, that is in joule, in Newton per meter square. Which we can roughly write it as uh, 15 into 10 to the power of 7 Newton per meter square, or 150 10 to the power of 6, which is 150 m Newton per meter square. First part is over. Now we have to compare it with the Young modulus. If we compare this with the Young modulus, that is 70, but it's not only 70. Like if I have to make them in the same unit, so it will be written as 2, 3. It's a Young modulus. Let's try to compare them. So it's roughly around 500 times more. So the modulus is 500 times more than the fracture strength. Okay, so this is what the comparison is telling us about. Okay, so with that we have solved this question number 12. Let's move back to the question number 13. According to Griffith, okay, let's do it one by one. Take one page. Okay. According to Griffith, any stress will cause a crack to propagate if given enough time. See, we saw this is a crack length and this is applied stress. Let us say my material is having the crack length something about this value. So what is there? In order for this is a safe zone. The crack will not propagate, it is an unsafe zone. The crack will propagate over here. What we found from here is that at this particular stress only, if the crack length, if the crack length for a given crack length, if the stress applied is more than this critical value, then only it will propagate. What this is telling that according to Griffith, any stress will cause a crack to propagate if a given enough time. No, it's not the case. Let's say I'm only applying this much, then crack is not going to propagate. Only if I cross this stress values, if I'm applying anything around this particular thing, then it's going to propagate. So the first one is false. The mechanical energy change due to the cracking is proportional to the square of the crack length, right? So this is, we know that mechanical energy change is proportional to the sigma square c square divided by m modulus. It is proportional to these things. So from here we can say the square of the crack length. Yeah, it is. So this one is true. Higher surface energy material are more resistant toward the crack propagation. See, this one can understand by intuition itself that okay, the surface energy is higher, so the energy required to create surface is more. So the crack will not propagate because propagation of the crack lead to the more surface energy. So the propagation of the crack lead to the more surface area. So correspondingly more surface energy. So it is more resistance. But one can also see this from the Griffith criteria. So here, if I'm increasing this surface energy, so now the fracture stress, the stress required to fracture the material will also increase. So from here also we can say that yeah, it's true. The Griffith original analysis was for the brittle material. No, it was for the sorry. Griffith original analysis was for the ductile material. No, it's for the brittle material. So this is false. To make it true, we can write the brittle. Okay. So the false, true, true, and false. Okay. Let's move ahead to the next question. Question number 14. Why did the aircraft designers switch from square to the round windows? To reduce the aesthetic for better aesthetic, to reduce the stress concentration at the corner, to decrease the minimum cost, to improve the visibility. See, we know that if we are having the maximum stress at the crack tip is given by the applied stress times 1 plus 2 root over a divided a is a cracking divided by rho is a crack tip radius. So the sharper the corners are, more value will be this. Sorry, the sharper mean that it will be the lesser the value it will be. So less value it will, so more applied. So the for given applied stress, this value will be more. So the maximum force which our material is going to so maximum stress which our material is going to feel is quite higher than what is applied if we just keep on decreasing, if we keep on making the corners to be the sharp. And that's the reason why from the square this was quite sharp, we changed to the circular window. Okay, now with that we have solved this question. Any doubt, please let me know. Let's move to the next question, question number 15. If the surface crack causing fracture in a brittle material is made twice as deep, the fracture strength will. So now the fracture strength we have to come in. It is given by the Griffith criteria 2 gamma e divided by pi times c. Here we can say that the fracture strength is proportional to the 1 over root c. So now if we are making the crack twice, if we are increasing the crack, so what will happen? Initial root over c, final root over 2c. So what we will get? The final stress will be equal to the is given by initial stress divided by root 2. So the stress required to fracture will decrease. This is more than 1, right? So initially if I was requiring sigma I, now I will require the sigma I divided by root 2. So the stress required to fracture, if we keep on increasing the crack length, the fracture stress required will decrease. So decrease by the factor of root 2. Okay. So with that we have solved this question number 15. Let's go to our final question, question number 16. The finer grain size, and we have to here comment on the ductile brittle transition temperature. To the final grain size, we saw in the class that it is decreasing the ductile brittle transition temperature because it was increasing that region, the ductile region. High carbon content. Since high carbon content, more brittle the material, we are increasing the ductile brittle transition temperature. FCC structure, it's since it is FCC, so there is no ductile brittle transition temperature, so it's good for the cryogenic application. Notches. If I uh, instead of this material, if I'm producing the notch in the material, so now what will happen? Make transition. No, I made a mistake over here. High carbon content, it will increase that is there, but it will also make the transition more gradual. So instead of when the carbon content was very less, the transition was like this. So now the transition will be get gradual. Again, the ductile brittle transition temperature will increase. That is there. Okay, so for this there are two things. So now for the notches, if I make the notches from here to here, so now what will happen that it is going to increase the ductile brittle transition temperature. It is option A. Okay. So with that we have solved this question number 16 and we completed our week 12 discussion. Let's have a final look on to the questions. Then some on the brittle and ductile fractures. We solve few numericals. True and false based questions. We solve few numericals based on that. Cross slip and these things like diffusion, like creep mechanism we talked. Creep life we talk about. What temperature creep is going to happen under the what condition. And then we talk about that, okay, the same thing, lead solder got creep at room temperature and other not got. So with that, and these are the list of the content that has been covered in this particular week. So with that, we are done with the week 12. If you have any doubt, please let me know. If not, we can conclude this. Before that, let me tell you that tomorrow we are going to have one final discussion on the entire course, where you can ask me any doubts which you feel from week 1 to week 12, anything. If any problem you are facing in the assignments and all, we can discuss those things also. So, and the timing will be the 10 to 11. So please be present between 10 to 11. Sorry, timing is between the 11 to 1. Between 11 to 1 we can discuss anything, whatever you like. Okay, so with that we conclude this class today, and let's meet again tomorrow. Bye bye, take care.